So it looks like everyone's back, most likely from lunch. Hope you enjoyed it. And hereby I would like to hand the word over to Timothée with his talk about Sling Content Distribution for the cloud. Let's welcome Timothée on stage.
Welcome, everyone, to this talk. First, a few words about myself. I am a software developer at Adobe R&D in Basel. Currently, I lead the development of the content delivery for AEM in the cloud. And as part of this effort, we actually built new implementation of content distribution that fits the cloud together with Christian, who had a talk this morning, and also Marius Petria, which you may know from the Sling community. In the open source world, I'm active as a Apache Sling committer and also recently as a Apache Sling PMC member. First, I would like to give you an overview of the distribution framework, a quick one. First, its purpose. So in a typical Sling CMS deployment like AEM, we divide the instances into an authoring environment and a publishing environment. And distribution framework is meant to distribute resources between those environments and within a given environment. The typical use case are the following. We can publish content from the authoring environment to the publishing environment. We can also sync user profiles and also group memberships within the publishing environment. So assume you have some users that log into a publish service. Their profile is going to be created there on this instance, but since there are multiple published instances in the publishing environment, you want this profile to be synced consistently on all those instances. So this flow supports that. And then we also have some basic support for user-generated content. And those three use cases, they map naturally to three distribution flows that are supported by Sling Content Distribution, or SCD in short. Forward, sync, and reverse. The sync flow is specific to SCD, but the forward and reverse flow are similar to flows that are well known in AEM, the publish flow and the reverse flows. The things that I'm going to share today actually apply for both frameworks, replication or Sling distribution. When we look at the implementation of those flows, we see a lot of queues today in the current implementations. There are queues for each source or target instance. Those queues currently, they are implemented using Sling Jobs queues. It has some nice properties to implement those queues that way. First of all, it works out of the box because the Sling Jobs queues leverage actually JCR to back the queue items. So JCR is available in every AEM or Sling instance that we would like to deploy. So that's nice. And also a nice side effect is that the backup and restore operations are for free for those queues because whatever we build for the repository applies for the queues as well. But there are some drawbacks with this approach to storing queues in JCR. First of all, maintaining the queues require a lot of small writes to the repository for some data that is meant to be relevant only for a few minutes maybe. So all those writes to the repository for large customers actually cause some write retention, contention, that can actually trickle down or impact the entire instances. What you will start to see with large customers is a larger and larger commit queue. So your commits gets delayed, can take minutes. You also see that the CPU will start to max out. What also is a negative side effect is that all those transient data structures that you have to write in the repository. They have to be collected at some point. And this increases the duration of the compaction cycle for the repository. Another aspect of the current implementation is that it uses point-to-point connections between services to distribute content or send actions from an instance to another. So this works, but it requires to configure an endpoint for every instance that we add in the topology. Due to those characteristics, changing the topology is actually quite difficult because you need to configure both the authoring environment and the publishing environment, and you need to do it in a coordinated way. You cannot just configure whatever on the authoring and something else on the publishing in any order. You really have to coordinate. This type of distributed coordination is hard to automate because a lot of things can go wrong, and you always have to have a fallback for anything that could go wrong. So this implementation is totally fine for on-premise environments where the topology is mostly fixed, but for the cloud, it's not ideal. In the cloud, we have actually a new paradigm that brings new requirements and also new opportunities. The first requirement, the main one, is to be able to scale horizontally the publish farm according to the load. So we know from fact that websites are used more during the weekdays, and maybe some days are busier than others than compared to the weekend, for instance, where we probably need less instances to serve our pages because the load is less. So the first requirement is to be able to do this, adapt to the load automatically without having humans to start instance or stop them or handling case that can go wild or wrong. The second requirement is to reduce the repository operations such that we avoid escalations that may arise from issues in this area, and generally to also simplify our operations of AEM by reducing compaction cycle, for instance, and reducing the escalations count. The third requirement, it's not due to the cloud, but it's due to the fact that replication is widely used, and it's been around for more than a decade. We could actually evaluate that a large majority of us leverage the replication APIs or extend the replication framework using APIs or hooks. So it was not an option to actually just drop the API and go for something totally new. Regarding the opportunities, actually the opportunity is that we can back the queues outside of the JCR repository. Why is this possible in the cloud? Because the cost that incur when we do this, which means selecting a queue system, setting it up, operating it, and maintaining it, is actually on the cloud provider side. It's not on the end customers that these costs will incur. So in this context, since we had to keep backward compatibility for the APIs, the first thing we wanted to do is to have a model of the distribution that we support today. And on-premise, it works like this. On author, we have one queue represented per publish service. And out of this queue, we send events when an item is added, removed, or just processed from a queue. We also allow via APIs to iterate over queued items, and we allow to remove any item from the queue or a group of items. We allow random access for that. On the publish side, we see that the content is eventually consistent, which means actually that the queues are processed at their own pace. So one publish may go faster than another publish, but eventually they reach the same state. Regarding the distribution model, in our new implementation, we could actually keep most of it. The only slight difference is that we don't allow to remove random item from the queues. We only support removing a range of items from the queue, and that range, the range has to start from the head. It's a different semantic, but it turns out we could not find really strong use case for allowing removing random items from the queues. So this distribution model should still fit the purpose. And now I would like to go a little bit deeper into the journal-based forward flow implementation. So the forward flow is the flow that most of us use. The other two flows, the sync and reverse flows, are a bit less used. So actually, currently, we have an implementation for the forward flow in Sling, but we don't have an implementation for the reverse and sync flows. We only have a design for that, but it's only on paper for now. So it's based on a journal. And what is a journal? Actually, it's an append-only log store. So it's a log where we can append messages at a tail, and we cannot remove messages from that journal, from that data structure. So the order of this journal is the same for every consumer. It's totally ordered. And the messages that we store have some properties. First of all, they are attached to a position on the log. And when you get two messages, you can actually compare the position and tell which one happened before the other one, or rather was stored in the journal before the other one. And that's a pretty strong property that we can leverage. Another feature from the journal is that we can replay messages from a historical position. That's something which not all PubSub messaging systems provide, but these systems like Kafka actually provide this ability pretty well. So I said that we cannot explicitly remove messages from the journal, but at some point we have to remove data, otherwise it grows forever. And the way this is done is by using a retention policy. If we take Kafka, it can be either count-based or time-based. In our case, we require a time-based retention policy of 7 days by default. Another thing we use from the journal is that we let the consumer manage their position on the journal. We don't expect a central point somewhere to manage the position for all consumers. If we look at the system view for this new design, we see that there is a journal in the center, and we stop sending point-to-point, issuing point-to-point requests between services. Instead, we exclusively use the journal to exchange information. The journal can support only small messages. The max for Kafka is 1 megabyte by default. So since we have to distribute large files, maybe video files that are terabytes long or large, it's a problem. And the way we solve this problem is by requiring a shared data store. So the large files, they remain in the shared data store, but we only send, in the journal, we only send a reference to that file in the data store. That's exactly how the binary-less support for Durbo and 5-volt works today. And actually, we use the same serialization format in this new implementation, and the same binary-less mode. 2 new agents have been added for this new design: a PubAgent and a SubAgent. So for this flow, the PubAgent runs on author, and the SubAgent runs on publish. It creates a lot of confusion, but we could not so far find a better mapping than this. The subscriber can subscribe to 0, 1, or multiple PubAgents by configuration. And the 2 agents are completely decoupled in the sense that the author can be started before or after the publish, or configured after or before the publish. The order in which you start those 2 agents doesn't matter. You will, at the end, reach a consistent state. So when we look at the PubAgent functions, we see that it handles the distribution requests, and upon them, it builds binary-less content packages in memory, and it appends the content packages to a topic dedicated to content packages in the journal. And I have to stress that it's only a single topic. So in the journal, we don't represent a topic or a set of topic per publish instance. We have only one topic per publisher agent. Another nice side effect of this is that, I mean, the PubAgent doesn't write on the author repository at all. So everything it does is computing content packages in memory and then persist them on the journal. The node store is not used on author, which is one of the requirements we had, and it can be satisfied that way. Then the PubAgent also has the ability to discover the set of sub-agents, and we will see later how it works. It's very simple. The next responsibility for the PubAgent is to compute the queues for each sub-agent. And it does that based on two informations. The first one is the last imported position that each publish service communicate to the PubAgent. And the second one is a cache of all the content packages that have been written on the journal. So it's actually not the entire collection of content packages. It's only those that are required to compute a given queue. So if a new request for a larger queue comes in, the cache will actually fetch the remaining, the missing part to complete the request. But in most cases, actually, the publish services progress at roughly the same pace. It differs definitely, but not in a wild way that actually the cache has to grow infinitely. And then regarding the sub-agents, it has a completely different behavior. What it does is that it consumes the content packages from the journal, and it applies them sequentially one after another. And the nice feature is that it imports them exactly once. And we can ensure that because we store the position in the repository, in the sub repository, where the sub-agent runs, sorry. So we store that in the repository, and we also import content. The way we ensure it's exactly once is that we use a single commit to update both the last imported position and actually importing the content. So it's atomic from that perspective, and that way we can ensure that packages are imported exactly once. Another responsibility is that it announces itself periodically. So it writes a ping message with its identity and also its last imported position, and it writes that on a dedicated topic for discovery on the journal. This topic is set up with a much shorter retention policy of maybe minutes, because actually it doesn't. We typically don't need to know the entire history of states for each sub-agents. We only care about the recent ones. And then there are two ways to report the status for each package import. So the first one is via the ping messages. The last imported position is contained in the ping message. And the second one is optional, and it allows, configured that way, sub-agents to send an explicit status message for every package it imports on a dedicated topic. So as I said, the retention policy is time-based for our topics. So the question could arise, how do we do if the retention policy is 7 days and we start an instance 30 days after the world has started for this environment, and maybe this instance starts to fetch packages from the position 0, the initial position. The answer is that we will lack a lot of messages, because those messages will have been garbage collected by the retention policy, removed. So to solve that problem, actually, we use the concept of a golden publish service. So it's exactly the same service as a regular publish that runs in the farm, but it has some small differences. The first one is that it's not exposed to the traffic, and so it doesn't handle requests. it only imports the content packages from the package journal. There are some nice features from this Golden Publish. The first one is that it's the source of truth for the content we publish. Eventually, all the published services in the farm, they will match exactly what the Golden Publish is. And the way we will also leverage the Golden Publish is to scale up. So when we scale up, we will actually need to add a publish instance in the publish farm, and we will do it by cloning the Golden Publish and simply deploying it in the topology. So if you remember, the scaling operations for the previous implementation were quite tricky. It required some coordination. But now, with this new implementation, scaling up is actually fairly trivial. You can do it without coordination by just starting a clone. And the clone of the Golden Publish doesn't have to be that much recent. It has to be just more or fresher than the topic retention policy of 7 days. So it's pretty nice because you can take clones of the Golden Publish asynchronously, and you can use those maybe slightly older clones to scale up, and eventually the system will reach the same state. So how does it work? When a clone, here it's the publish n+1 starts, it starts to import content packages from the journal, and it starts at a specific point. It starts from the last imported offset that has been carried over via the repository. If you remember, we store the last imported position, in the repository. So that's what it does. And when this service figures out that there is nothing new to import for a configurable amount of time, then it decides that it's ready, and it marks itself, or it declares itself as ready. And we typically run this in an orchestration container like Kubernetes. And Kubernetes is able to detect that signal, and when it's ready, it's actually going to expose this new publish service to the world, to the traffic. So as you can see, the distribution actions could be accepted at any time along the way. We don't have to stop processing replication actions when we scale up. And also, we can scale up without coordinating anything. We just add an instance from a fresh enough clone, and that's it. Another aspect that we wanted to improve is the following. Unfortunately, we cannot avoid blocked queue situations. Maybe some of you are familiar with those, if you have to do some operations with AEM. So we cannot, with this new design, avoid all blocked queue situations. Fundamentally, some of them are due to badly configured authorizations. So we cannot do much about it. And what we wanted to do, though, is to improve the consistency when we handle those cases. To do this, we have divided distributing in 2 phases, the staging phase and the rollout phase. The staging phase consists of distributing only to the Golden Publish, and the rollout phase consists of distributing to the entire farm of publish services. During the staging phase, we can actually remove items from the queue. We can edit the queue. That's fine. So if the queue is blocked, as usual, we can have an admin that comes in and remove the problematic item from the queue. That's supported. At some point, we may also add the automated mode to handle those cases, meaning that after a configurable amount of retries, we could quarantine the problematic content package automatically and then just move on. That's one option. But for the rollout phase, we don't allow to edit the queues. So we do actually something better. We don't allow to edit the queue, but we monitor the queue. The Kubernetes has some service that monitors the queue. And when it figures out that more than a configurable amount of retries have failed for this queue, then it takes the decision to actually remove the publish service from the topology and replace it with a new clone that starts from the Golden Publish. So this way, actually, we handle the errors that happen on rollout automatically. Now, this new design is actually integrated with AEM. The way we do it is that we use the bridge that allows bridging a replication agent to a Sling distribution agent. So by default in the cloud, what we could do is configuring the AEM publisher agent to use the journal-based distribution agent for transport. This way, we will actually support the replication API while still using a cloud-ready implementation for distributing content. So some differences, we would have only one replication agent that supports n published services. That's one. And the second one is that we will eventually probably get rid of the replication UIs in favor of the Sling distribution UIs to clear and remove operations. In other words, the bridge goes only one way. It doesn't goes back the other way. The design is actually portable. Currently, we have a distribution messaging APIs that is defined in the project in Apache Sling. It allows to port the design fairly easily on various backends. The main one is Apache Kafka. We have an implementation in Apache Sling as well, and that Apache Kafka was actually the main backend we used to develop this. But we identified the requirement for a journal for portability, and we figured that actually it could be ported to any RDB fairly easily. And we also have some POCs, proof of concept code internally to Adobe that shows it can be implemented easily on MongoDB as well. There is, you've seen this morning the OSGI track where some RFP are actually developed for messaging, and I think that Christian is working on some improvements that may allow to replace these distribution messaging APIs with OSGI APIs at some point. But currently, it's portable that way. You may also want to check it out. So I have this project here on GitHub that describes all the steps you need to set up a local Kafka deployment, and also start a publish and author Sling service that is already configured to talk to this local Kafka service and already configured to use the journal-based distribution. So you may want to have a look at this if you're interested. And do you have questions? Yes?
For example, if you have addressing content packages which override, Hi, my question is if you have a queue which addresses, contains content packages which overwrite themselves, is it a way to optimize, like catching up from last position to the last, omitting some packages?
You mean to skip packages?
Skip packages
oh,
which
yeah.
you know that will arrive, the same content package will in another version will arrive later in the queue.
Okay, so skipping packages is exactly how we do it for the editable queues. So we have a dedicated topic where we send commands, and some of those commands are grant the ability to remove some specific offsets, but we limit those editable queues for the golden publish queue. Does that answer your question? Or vaguely.
No, I think about editors which usually publish not ready for publishment content, and come back 10 minutes later and say, oh no, I didn't want to publish that, I published the same package
perfect.
again, and then you could optimize the installment in the subscribers part. So like I see forward in the queue, there is a content package which overrides a content package which I just am about to install, so I could omit that and just take the next one.
Okay, so you have the ability to remove content from the queue when it's in the golden publish queue, but you cannot remove anything when it's in the rollout phase. That's one of the, I mean, it's a limitation of the design, but we get some pretty nice features out of it. It's the content that we publish is consistent, which is pretty nice. In the past, with the Sling Jobs implementation, we actually give way too much power because you can edit individual queues, so you can reach different state on different published services. So the best compromise we could find is that one. Okay, thank you.
Hi. Was not clear for me how you deal with user-generated content when they live on the published instances, how you roll out those content to the golden publish.
So currently, I think I touched that a little bit, or vaguely. We don't implement user-generated content flow, so reverse replication flows, but we have a design for this. It's anyway not the way we advise handling a large amount of user-generated content. For that, we have some better suited offerings like AM communities. I think it goes like this. And it's essentially a central store, and it's much easier. We delegate a lot of issues to this central store. But we will anyway support reverse replication, or a reverse flow for really simple use case when you just have to move back a single asset or a PDF or something that has been published on, that is available on Publish and has to be retrieved or fetched on Author. But currently, nothing concrete on this side.
Hey, is there any support for any advanced support for moving resources around in the resource tree? Because currently, if I remember correctly, that is still implemented as a delete and then add, or the other way around, which is obviously a lot of overhead.
Yeah, so we don't support at that level, at the replication level, moving pages from a location to another. So this would be in sites or in assets UI that you could do that. But then, unfortunately, you still have to actually press the button to replicate the source and the target where you moved your content. So we don't support the move operations at that level, I'm afraid.
Another question to follow up on this reverse replication topic. So the AEM, you mentioned the AEM communities, and that has the user sync. So that is basically one of the things that are not implemented yet, I suppose. But like, would you just use the status quo today, or what would you recommend?
So AM communities, it uses its own database for storing user profiles, but the actual, you still need to log into the publish instance, and it leaves some traces in the publish repository, and to sync this profile, we still need SCD. We simply didn't implement the sync flow for SCD yet, but eventually that's the plan. We will support that flow. So, yeah.
Okay, thanks.
So you mentioned something about the shared data store being needed. We had long conversations with Adobe support, and they told us that they cannot support shared data stores. They said that they can become corrupt due to network latency and things like that. So is this something that is really needed to make this function work? It's
so
about the assets being replicated?
Okay. So with this new design, it's a strong requirement, yes, to have a shared data store, because journals are typically capped. The message size is really capped, so we cannot think about sending 1 terabyte over, I mean, inline in a single message. So for this new design, it's a requirement. Now, I don't know in what stage you are with Adobe, but definitely replicating using a shared data store is supported today with the Sling Jobs implementation.
Okay. Thank you very much.
Thank you.